The enigma of quantum physics. Quantum physics challenges our traditional understanding of reality by introducing concepts that defy classical physics. It describes the behavior of particles at the smallest scales, where the rules differ dramatically from the macroscopic world we experience daily. This branch of physics forces us to rethink fundamental notions of reality. Quantum superposition. Multiple states simultaneously. One of the most perplexing aspects of quantum physics is superposition, where particles can exist in multiple states at once. For example, an electron can be in multiple locations simultaneously until observed. This concept challenges the classical idea that objects have a single, well-defined state at all times. The observer effect. Reality and perception. The observer effect suggests that the act of measurement affects the system being observed. In quantum experiments, particles behave differently when measured, leading to the conclusion that reality may be influenced by our perception. This challenges the notion that reality exists independently of our observations. Quantum entanglement. Instantaneous connections. Quantum entanglement describes a phenomenon where particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of distance. This spooky action at a distance defies classical concepts of space and time, suggesting that particles can be linked in ways that transcend traditional physical limits. The uncertainty principle. Limits of knowledge. Heisenberg's uncertainty principle posits that certain pairs of properties, like position and momentum, cannot be simultaneously measured with arbitrary precision. This principle introduces fundamental limits to what can be known about a quantum system, implying that uncertainty is an intrinsic aspect of reality, rather than a limitation of measurement tools. Wave-particle duality. Dual nature of light. Quantum physics reveals that light and matter exhibit both wave-like and particle-like properties, a concept known as wave-particle duality. This duality challenges classical physics, which treats waves and particles as distinct entities. The ability of particles to display both characteristics depending on the experimental setup questions our understanding of the nature of matter and energy. Quantum tunneling. Crossing barriers. Quantum tunneling is a phenomenon where particles pass through energy barriers that, according to classical physics, should be impenetrable. This effect has practical applications, such as in tunnel diodes and nuclear fusion, but it also challenges our classical understanding of how particles interact with energy barriers. The role of probability. Indeterminate outcomes. Quantum physics often deals with probabilities rather than certainties. The behavior of quantum particles is described by probability distributions, meaning that outcomes are not deterministic but probabilistic. This probabilistic nature suggests that reality at the quantum level is fundamentally indeterminate and subject to chance. Implications for the nature of reality. Quantum physics forces us to reconsider the nature of reality. The principles of superposition, entanglement, and uncertainty suggest that our intuitive understanding of a deterministic and orderly universe may be incomplete. Instead, reality might be a complex interplay of probabilities and interconnected phenomena. Philosophical and scientific impact. The challenges posed by quantum physics extend beyond science into philosophy and metaphysics. Questions about the nature of reality, consciousness, and the limits of human knowledge are deeply intertwined with quantum theory. As research continues, quantum physics will likely keep influencing both scientific and philosophical discussions about the fundamental nature of existence.